All right, and this is the lesson 1.4 notes on perimeter and area in the coordinate plane. So we'll start with a little bit talking polygons and some vocabulary that goes along with that, and then we'll look at what does it mean to find perimeter and area in the coordinate plane. So make sure you're adding some of this vocab to our notes. When we talk about a polygon, all right, a lot of stuff going on here. The big stuff. What is it? It's really just it's a bunch of segments all connected at their endpoints. All right, so if I've got segment BC connected it to segment CD and so on, we end up with this closed figure. So that's part of it. Closed figure in a plane in 3 or more segments. We basically switch from calling the segments now to sides, and then instead of calling them endpoints, C and D, we call them a vertex, or the plural would be the vertices. All right. Naming a polygon, we name just in order, consecutive order. It doesn't have to be alphabetical, it doesn't have to be clockwise. And we would just say, you can see it right here, polygon A, B, C, D, E. That's one way to name it. We could call this polygon C, D, E, A, B. Any order you want, as long as you don't jump around. I couldn't go A, C, E, B, D. That would be an incorrect way to name this polygon. So that's the intro. What is a polygon? How do we name them? Some of the parts of it, the vertices, the sides. Okay, it's basically putting our segments together to make a closed figure. All right. Next in our notes, let's add, if you need to, pause it here and add these names of common polygons, or at least polygons that we'll work with this year. A lot of these I'm sure you are definitely comfortable and familiar with. 3-sided figures called a triangle, obviously. 4-sided, not a square, not a rectangle. This is more of a broad category, the quadrilateral. And it goes on, a lot of prefixes going on here, a lot of things we've heard of. Octagon, 8 sides. The couple that maybe you're not as familiar with, 7 is a heptagon. 9 is a nonagon, and then 10 and 12, they sound similar. It's decagon for 10 and dodecagon for 12. You notice we skipped over 11. It's a funny name. It doesn't come up very often in ours, so we're not required to know that one. Basically 11 and then 13 and on, we would name them by their side. So for example, an 11-sided figure, we'll end up just calling that an 11-gon. Okay, 13-sided figure, we'd call 13-gon, 14, and so on. Okay, forever beyond 13. So that's what this bottom piece is talking about here, the n-gon, basically the number of sides beyond 12. We'll just use the number of sides to name it. 15-gon, 20-gon, 100-gon, talking about the sides. All right. Okay, and then the last piece of vocab that goes along with this section is the idea of a concave polygon versus a convex polygon. So I think we've got a good illustration here. Concave, the way I remember it, is, it's got a portion of it that caves in. So as I'm counting my sides here, this is a 1, 2, 3, 4, 5, 6-sided figure. So it's a hexagon, but it's caving in at this one spot here. Whereas this 1, 2, 3, 4-sided figure, this quadrilateral, doesn't have that cave-in going on. So that's a little trick for remembering. What's going on with these lines here? This is the more formal definition of a convex polygon. It basically says that the line that contains the sides does not pass through the interior. Okay, so if you look at every one of these red lines, I'm just basically extending the sides. So I'm going to extend this side of the quadrilateral, extend this side. When we extend all the sides, the lines that we're making just stay right on top of the sides. They pass right through them. They never go into the figure, where that's going to be true here for a lot of the sides. So if I add some of these other sides here, definitely this side, there's the line, just like before. Here's another line here. It's containing the side. But there are a couple sides that if I extend a line and I say, oh, wait a minute now, hold on, we're passing through the interior of the polygon, that's what makes this a concave polygon. So it's a little confirmation, a little way to check to verify, hey, is this concave or convex? That's one thing you could do. All right. So using all that vocab and terminology that we just talked about, classify each polygon by the number of sides, tell whether it's concave or convex. All right. So we'd look at, let's do the first part, classify each one by the number of sides. So that's you telling me, hey, how many sides does this have? I count 1, 2, 3, 4 sides. So this is a quadrilateral. So that's how I'm going to check. Have you learned your classifications by side? Okay, have you learned these different names? We've got, let's see, let's just do this one right away. 1, 2, 3, 4, 5, 6. So this is a hexagon. Okay, 6 sides is hexagon. And then is it convex or concave? So here we can see what we had just talked about. Here's my check that if I extend this side, whoops, we're passing through the polygon. That makes this concave. Whereas here, every side that I try to extend, I always just kind of stay on the sides of the polygon, which makes this convex. All right, so straightforward application of some of the vocab we just covered. Moving on, so I think we can cross off, we can check off classify polygons. We talked about some of the vocabulary that goes with them. Let's go on now to talking about perimeter and areas of polygons. Not all of them. We'll focus on some basic polygons, some triangles, square, rectangle. All right, so you can see here, definitely add these formulas to your notes. We've got different ways of finding perimeter. Perimeter, remember, as just a recap, we didn't officially formally define it here. Assuming this is a concept that you've covered in previous courses. Perimeter is essentially the sides of a polygon, the side lengths of a polygon all added up. Now there's some shortcut ways to think about it, especially like in a square when we know all 4 sides are the same. Instead of saying s plus s plus s plus s, we can just 4 times s. Same thing with a rectangle, L plus W plus W, well, 2L plus 2W. So that's where that's coming from. For a triangle, keeping it pretty generic, we don't necessarily know that any of these sides are the same, so we're just using different letters for each A, B, and C, A plus B plus C. Add all your sides up, there's your perimeter. Let's jump over here back to square and rectangle for area. Area, remember, is the amount of space or the amount of cubic units, I'm sorry, that's volume, the amount of square units we can fit inside a figure. So if we were to look, how many of these perfect little squares can we fit inside this square? To do that, we'd look at length times width or side times side, whereas with a square, again, we have side times side. The shortest way to say that would be side squared. So if I know one side, I can find essentially the area and the perimeter of it. That's all I need to know is a single side. For a rectangle, we're talking length times width. You may have heard it as base times height. Same concept. Triangles can be a little bit tougher, trying to decide what should I call my base, what should I call my height. The height, a lot of times, isn't one of the sides of the triangle, but it could be. So here's a good illustration of we've decided to call this our base. So then the height then is the third vertex, right? I've got 3 vertices on this triangle here. Well, the 2 vertices that make up the base, whatever side we want to call the base, are right here and right here. Where's the third one? Right up there. So when I want to find my height, I go from that third vertex kind of straight down and hit my base, and then that's the number I need to use for my height. There are some alternative types of triangles that we might see. We could potentially see a triangle where, say we call this our base. Our height, remember, we just talked about, here's vertex 1, here's vertex 2. Where's my third vertex? It's up here. How do I get straight down to my base? Well, now we end up with the side of the triangle right here ends up also being the height. All right, so that's a special type of triangle that we'll spend a lot of time with, but the height we've seen could pass within the triangle here. It could end up as being one of the sides of the triangle. And actually a third situation could potentially be a triangle that's situated like this. Maybe we decided to call this our base. And now my height, where's my third vertex? Way up here. How do I get from this point right here to this base without, and staying perpendicular? My height actually has to travel on the outside of the triangle. So a couple different looks. Triangles are a little bit more broad if we're just saying triangle versus square versus rectangle. Those are super specific types of quadrilaterals. Triangle, we're trying to keep it a little bit more open here. So 1/2 base times height. I guess I kind of skipped over that part. There's our formula. 1/2 times the length of your base times the height. That's why that number is so important. We need that height. Okay. So the last thing we have to do is to look at how are we going to use these formulas in a coordinate plane. That was the last big idea, find perimeters and areas in a coordinate plane. So let's run through just a couple quick examples, and I think we should be good for the lesson. So finding the perimeter and area of triangle ABC with vertices A, -2, 3, B, 3, -3, and C, -2, 3. So it's asking us for both perimeter and area. This question, or any type of question like this, involves if it's asking us to plot or find the perimeter area of a triangle, I think I want to see it, right? It's hard to do this if I can't see the figure. So it all starts with a good, accurate plot. Let's go -2, 3. There's my point A. We'll label them. B is 1, 2, 3, 1, 2, 3. B is 3, -3. So I'm down here at B, and then C ends up being -2, -3. So there's my triangle. Let's connect them. Like I said a second ago, make sure we're plotting accurately. The hardest thing I see sometimes is somebody does a perfect perimeter and area problem of the wrong triangle. You misplotted, and then your perimeter ends up being incorrect. Your area is incorrect because we plotted the wrong point. So take your time and do that part accurately. All right, let's start with perimeter here. Whoops, how are we going to find perimeter? Well, perimeter is essentially adding up all our side lengths. What I'd like you to do is tell me your different side lengths. All right, so I think some of these are easier to find than others. If I want to know the length of AC, like AC is a vertical segment, which I can count the units and be totally fine. So I'm talking AC has a length of 1, 2, 3, 4, 5, 6. 6 units long on that one. Great. I can do a similar process with BC because it's a horizontal line. So whichever way I count, I know that BC has a length of 1, 2, 3, 4, 5. Awesome. The last thing we need here is the length of segment AB. Now, unfortunately, I can't just start kind of counting from A to B and go 1, 2, 3, 4, 5. So, it doesn't work like that when we have a line that's not vertical or horizontal. So I do actually have to go through and use what we talked about last lesson, the distance formula. Let's see if we can squeeze it in here. Remember, it's x2 minus x1 squared plus y2 minus y1 squared. All right. Which point should I use? A, B, or C? Right. We've got 3. The distance formula is set up to find the distance between 2 points. So we got to make sure we're working with the correct ones because we were looking for the length. Whoops. Because we're looking for the length of segment AB, that's the last piece of the puzzle here, we definitely need to be working with points, the coordinates for points A and B. All right, so I'll go a little bit quicker here with our distance formula. It's something, if you need to review on, go back and watch the lesson 1.3 notes. See if we can squeeze this out here a little bit. So we're going to go x2 minus x1, so 3 minus -2, square it, and then -3 minus 3 squared with my y2 minus y1. This ends up being 5 squared here. We end up with -6 squared here. Remember, we're still under that big square root. 25 plus 30. Oops, probably definitely keep a parentheses around that. 36. And then finally, the square root of 61, which we do need to get down to a nearest tenth of a unit here. Sorry, I just had to grab my calculator because I don't know that one off the top of my head. The square root of 61 ends up being about 7.8. All right. So it's a little bit of work there. I'm keeping track of my distance formula, trying to stay accurate. So we end up with 7.8 units for our length of segment AB. Last thing, just don't forget, hey, we did all that work. What is the actual perimeter? So our perimeter of this figure is 6 plus 5, which is 11, plus another 7.8, 18.8 units. And because it's just units, it's not anything inches or centimeters or anything like that, I'm okay with us just leaving it as 18.8. All right, area. Let's switch over because we checked off perimeter, done. Let's do area of triangle ABC. Area, I think, ends up being a little bit less work because we've kind of done a lot of it already. I think we can fit it in down here actually because, like I said, we're going to use that formula 1/2 base length times height. I think a very strategic base for this particular problem would be to call this right here our base. So going back to some of the figures we just made on the previous slide, if I call this my base, that's a B, but I know that BC right here is 5. So I'm going to start kind of filling in some of this formula here. 1/2 is just, that's part of the formula. BC, our base, is 5 units long. The only thing we're missing here is our height, and this is one of those ones. Remember, I got to get to my third vertex, right? Here's vertex 1 and 2 that are making up my base. Where's the third vertex? Right up here. And if I'm bringing it straight down to my base, we know that length as well. So AC ends up being 6. Nothing really else to find other than crunching those numbers. So the area of our triangle ABC ends up being 1/2 times 5 times 6. 5 times 6 is 30. Cut that in half. It would be 15 square units. It's up to you. I'm not going to require, again, just because it's no units, you can leave it as just 15, and with the understanding that we're definitely working in square units. So there we go. There's an example. There's a triangle example. Let's do one more. I know it's another triangle example. Just to maybe go through some of those different looks that we saw here and here. Square and rectangle, obviously, the process would be the same. I would plot my points just to, and this isn't this problem, but just say I plotted my points. I found a rectangle. I could do that same stuff we just did, saying count my spaces and say, oh, my perimeter is 1, or my length is 1, 2, 3, 4, 5, 6. 1, 2, 3. All right. 6 plus 3 plus 6 plus 3, and figure out my perimeter and do length times width. So I just wanted us to at least mention how we would do a square or rectangle. All right, so just kind of repeating the process here. It's not identical, so let's just follow with me here. The point 1, 1, 2, 3. The point 1, 2, 3, 4, 1, 2, 3 for E, and then point negative 1, 2, 3, 4, 1, 2, 3 for F. So D, triangle D, E, F. I think perimeter-wise, just as I'm plotting in here and starting to take a look at it, we might have our work cut out for us. I think the quickest one here, let's just kind of set up our perimeter section. Perimeter, FE is probably the quick one, right? Where it's a horizontal line where we can count 1, 2, 3, 4, 5, 6, 7, 8. So 8 units long on FE. We're gonna have to work though for DF. Let's do our distance formula right away for that one. So from D to F, how long is that? Make sure we're working with D and F. Okay, so I'm gonna, again, we're using that same distance formula. I'm not gonna write the whole thing out again. We're doing negative 4 minus 1 squared plus negative 3 minus 3 squared. We'll end up with negative 5 squared here plus negative 6 squared here. 25 plus 36. Hey, look at that. 61. We just wrote this one a second ago. So 7.8 units again. Kind of a coincidence there. So, DF ends up being 7.8 units. Just for space purposes, I'm going to clear this off here, and so we can fit in our work for us finding out. We got one more to do. We've got segment DE. Let's figure out how long this one is. Same thing, using our distance formula. So I got to kind of clear off here. I don't want to repeat that process. That's just going to tell me the same thing. So we want to be working with points D and E this time. So we'll go to our big square root here and go 4 minus 1 squared, and then negative 3 minus 3. Whoops. Negative 3 minus 3 squared. 4 minus 1 is 3. Negative 6. So we end up with, let's see, 9 plus 36, the square root of 45, which this one I do have to crunch on the calculator. Second square root 45. We end up about 6.7. So not as clean. We ended up with 2 distance formulas on that one. But in the end, it's the process for finding perimeter of a triangle says add up all your side lengths. So we end up with 8 plus 7.8 plus 6.7, 22.5. Nice. She kind of worked out to a decent number there. So there we go. There's our perimeter. Same kind of process going on for perimeter. A little bit more work with a second distance formula there. Last thing we got to do for the lesson. Area. Again, I think just because of what we found already and what we kind of know and what we've talked about, ends up being slightly less work. There's no distance formula involved. I think another strategic base would be to call FE our base because it's a nice clean number. It's horizontal. I can count. It's 8. So we're ready to start filling some stuff in here. Let's call 1/2 times base. This is our base, which we already know from before, is 8 units. Now the height is what's different in this one, right? It's not my side length. It's not DE. It's not DF. My height ends up being, remember, same process. Where are my endpoints? Where's my third endpoint? Way up here. So how do I get from right up here down, where I'm drawing it up? That's my height. So I guess a takeaway would be if you end up with a horizontal base, we should end up with a vertical height, which is a good thing to know. That's nice. It's helpful. It's quick. It's one that we can count. So I just need to count units. 1, 2, 3, 4, 5, 6. So we end up with a height of 6 there. So in the end, 1/2 times 8 times 6. 8 times 6 is 48. The area of our triangle is 48 divided by 2. 24 square units. All right. So there's a decent look. If you ever end up with a triangle that's maybe not a quote unquote flat or horizontal base, you can always turn your paper to maybe find one that's horizontal. For example, let's say I know it's not this one here, but I graphed a triangle that looked maybe like this, and we're trying to decide where do I want to go with my base, what should I use? I'd be looking at either rotating my paper or saying, hey, you know what, this is a vertical line now, let's call this our base, and then I can end up using that for my height. So don't feel like you always have to use the base that's on the bottom as you look at it. You can rotate your paper and use any side you want to be your base. Pick a convenient one so we can maybe do some counting like that. Okay. So I think we've covered all our big ideas. We can definitely now find perimeters and areas of polygons, mostly triangles. That's what we've worked with, but I would definitely count on you to be able to scratch out an area or perimeter of a square or really any other type of figure. Well, maybe not area. So anyways, that's our lesson 1.4. I will see you in future lessons.